Okay, this is a bit of a marathon, but the next model here is the model that I call differential equation problems. All right, so differential equation problems, I like that a lot, but they have certain characteristics that, if you remember them, they're not that hard to do. Okay, so let's see what we got. We have a differential equation that looks pretty complicated. And then we have a particular solution to this differential equation. That's the initial condition that goes to 1, comma 0. Write an equation for the tangent line, tangent to the graph at the point. Use the tangent line to approximate f of 1.2, and then find y equals f of x. Find the actual equation that fits both the differential equation and the initial condition. Okay. So the most important thing to snap to in your mind for differential equation problems for this model is always separation of variables. So separation of variables, which entails separating the dy and the dx and put all the parts of the function that include y on the side where the dy is, and all the parts that include x on the side that where the dx is. So this is also called separable differential equations because, you also have situations where you can't do that, but luckily that's not part of AP Calculus AB. All right, so let's write the equation down here um, and then do that step. But alas, okay, so hold on a second. What this preamble, this prelapse here is only going to be used for B. So let's start in the order of the problems that are given. For A, we just need an equation of the tangent line. So an equation of the tangent line generally is shaped like this. Y minus y0, the initial y, is equal to the slope, and then x minus x from the initial condition. So we already have most of this. In terms of the actual thing here, we could fill in already this. Y is 0, right? 1, comma 0, the y is 0. And then the slope is dy dx at x equals 1 and y equals 0. And then x minus the initial x, and that is 1. So there. So then the only thing we need to find is actually this thing. And we find this particular slope just simply by plugging in the y and the x and the y of the initial condition into the slope formula that we were given here, right? So that dx dy dx at x equals 1 and y equals 0 is actually e to the 1 times 3, no, sorry, e to the 0, of course, right? Y is 0, x is 1. So e to the 0 times 3 times 1 squared minus 6 times 1, right? Well, e to the 1 is 1, and then 3 minus 6 is -3. So that equals -3. So now we can complete this. So -3 is what's missing here. So the equation for the tangent line is y equals, I could say y tan here just so I don't get confused later. Y of the tangent line is -3 is the slope, and then x minus 1 is that. And let's just simplify that to put it in a normal format here, -3x plus 3. Okay, so now we use this equation of the tangent line to approximate f of 1.2. So f of 1.2 is approximately the same as y tan of 1.2, and that is negative 3 times 1.2 plus 3. That is negative 3.6 plus 3. And that is negative 0.6. And that is A. All right. So now let's go to the second portion, which starts with my explanation of and my emphasis on separation of variables. So I have, let me write it out here. I have dy dx equals to e to the y times 3x squared minus 6x. And so now I have to separate the variables to have all the x's on one side and all the y's on the other side. So I multiply by dx and divide by e to the y. So I get e dy over e to the y, and I'm just going to put this here as e to the negative y, right? Because this would be below the, it would be a fraction, and I'm just going to make it a negative exponent here. Okay, so that's my y side, and then on the x side, I have 3x squared minus 6x dx. That's on the right side. So this is the most important step, is separation of variables. If you don't do this right, and if you don't do this, if you don't understand that you need to do this, you're basically not getting any of the points for this b here, and there's lots and lots of points to be gotten. So this is the most important piece of the puzzle here. And then the next piece of the puzzle is, so let's organize this a little bit more better here. Again, e to the negative y dy is equal to 3x squared minus 6x dx. So I'm going to end up finding the integrals of both of these. And that is the next step that I need to do here, right? Integral and integral. So now I find antiderivatives for both sides. Let's start with the easy side. This here is going to be x cubed divided by 3. That eliminates the 3. This here is going to be x squared divided by 3. That's 6 over 3. That's 2. And then plus c over here. And over on this side, what do I get here? So this is slightly more convoluted. I get e to the negative y, but then I have to multiply this by the inside derivative to get this. So actually, to make up for that, I have to make this negative here. So negative e to the negative y is the antiderivative of e to the negative y. Again, to convince yourself of that, just always, if you have a little bit more complicated antiderivative, just always go the inverse, just test if you got it right. So if you differentiate, you find the derivative of e to the negative y, that's e to the negative y times negative 1, which is the inside derivative, and that times negative 1 cancels this negative 1 and gets you positive e to the negative y as the derivative of this. So we have the correct derivative of here. The correct antiderivative here. All right, so that's our antiderivatives. Now, at this point, we're going to apply the initial condition to solve for c, to find the c that we need. And doing this will give us plug it in. Okay, plug in the 0 for y and 1 for x. So negative e to the 0 is equal to 1 cubed minus 2 times 1 squared plus c. So I have just numbers, and the c is the only variable here. So this here is going to be negative 1 is equal to 1 minus 2 plus c. Shuffle all the numbers over to that side, means I have, did I do this right? Yeah. Yeah. So I have minus 1 is, that means c equals 0. That's, I must have made some mistake here. Let me double check. Let me double check on this. C is not usually 0. I'll check this. So we have, did we do this right? Yes. Did we do this right? Yes. Did we do the integration right? X cubed is 3x squared. Ah, here's something wrong. There's something wrong here. Divided by 6 divided by 2 is not 2. That's actually 3. So I don't know if you generally have to be worried if C is supposed to be 0. It could happen. I suppose it could happen, but it just usually doesn't. Anyway, so the correct antiderivative of 6x is, of course, 3x squared, and the negative is in front of that. So that makes this here a 3. Let me do it right. It makes this here a 3, and this a 3. Let's fill this in correctly. 3 and 3. And that gives us, so -1 minus 1 is -2 plus 3 is 1 equals C. All right. And now I'm going to continue from here with the +1. So now I'm going to go back to -e to the -y is equal to x cubed minus 3x squared plus 1. And now I have to continue to isolate the y because I want to have a function there identifying y. So let me move the negative over. E to the -y equals negative. I'm actually going to just multiply this in, so it's not going to confuse us later. So let's do negative to each of these is x cubed plus 3x squared minus 1. Now I'm going to take the logarithm of on both sides. That gives me y, negative y equals ln of negative x squared plus 3x, sorry, cubed plus 3x squared minus 1. And that gives me then my y as negative ln of negative x squared, x cubed plus 3x squared minus 1. All right, so that is my particular solution to the differential equation that passes through 1, 0. And that's it. Let's check our results. Okay, the first one is negative 0.6. Here, check how you're getting the points, right? 3 points available. Dx at point 1, 0, tangent line equation, and approximation. So 3 pieces, right? We got the first one, evaluating dy dx at the point. Then the equation for the tangent line, where you use this slope here and use the point to make the equation happen, and then use this equation to find an approximation for f of 1.2, and that is negative 0.6. I think we got all of this. Yeah, we got all pieces of that. And then the second part is separation of variables. Gets us this. Then we find, so this is the separation of variables, finding the antiderivatives. That's this. Constant of integration gives you a whole extra point. The antiderivative is actually 2 points, right? Constant of integration is 1 point. Use the initial condition to solve for C is a point, and then solving for Y is the last point. And this is our last expression here that is on the next page. Y equals negative ln negative x cubed plus 3x squared minus 1. So we got all this right. And then see the notes here. This is really important. You can get only maximum 3 of 6 points if you don't have the constant of integration, because if you don't have the constant of integration, you can't do any of the other ones here below. So you can only get the 3 top points, and you get no points at all if you don't get the separation of variables. If you don't do it, or if you don't do it right, you get nothing. You lose 6 points here. So it's really, really important for this model to keep in mind separation of variables.